Are we online? We may or may not be. I think we're online. Okay. So I left off yesterday making RAM. I just finished wiring it up. It's all addressable. We've got 16 nibbles. Wait. Hold up, we don't. We only have 14. No, we have 16, never mind. I thought for a minute that 0 was not working. Not 0 is good. This isn't quite done. I might as well finish off the reset lines. Oh, wrong one. Oh, that's nice. Can just connect it up. I was looking at Logism, but oh, it's Silverclad. You know, I have to redo everything again. So I probably won't do that. Well, and it's also depreciated in like 2014. I could continue developing it. But you know, probably unlikely. If we move one of these, oh no, it doesn't. I mean, that's good now. Got the switch fully set up. That means back in our ALU, we can add heaps more instructions. I'll use the same switch for the CPU. Yeah. So I started making a clocked flip-flop. And what this does is... Oh, well no, I made the clock flip-flop. So it's like the flip-flop from before, but you set and then you pulse the clock. It just uses these 3-state buffers, like transistors, to allow the signal through. But that, it's quite rudimentary. Well, simple, but that will allow us to build a counter, which by using these, we should be able to make a counter. Has one input here, J and K. It's a JK flip-flop. think I need to make it T flip-flop. T being toggle. Like this. Oh, hello. Railroad Gaming. Hello. I suppose I can just invert the output. And if I then go to no, that doesn't work. Fair amount of Lego stuff. Massive Minecraft project. Oh, we have a Minecraft server as well. Asher Bika, hello. I have no idea how I'm gonna get this to work. And I'm just sending him pulses, but it will just randomly flip. Like, we need. Let's think. So, if the output Yeah, hold on. So we just have the reverse of the output is going to be the new input. And then we just need to reset and then pulse the clock. So if I do it like this, yeah, like this should work. Oh, it almost works. But still, there's still random variance. Hmm. Joeen Floors. John Wiener. John Wiener Floors, hello. Third party stuff. We just put the opposite in. But why is it triggering it a second time? Do I need a third? Does it want another clock pulse? I mean, it's working kind of more reliably. Just I say that, it stops. If let's see. If we just hook it up to a clock. It's preferring on rather than off. Where the heck is it? It's over here. Wait, they're all pulsing at the same time. That's not what we want. Oh. Okay, never mind. I thought it was different. We need... I mean, if we put knots on this. I can't even tell anymore. Well, let's just manually hook it up for now. Let's get rid of this. Okay, so we want to set. Hold down set, pulse the clock. Let go of set, pulse the clock. Wait, so we just need to trigger these both at once? No, reset and clock. Why does it get stuck there though? That's what I'm wondering. Okay, so say reset, pulse the clock. But how do we know? Unless... Wait, we always reset when it's there, right? When it's high. So surely we can just do like that. Three-state buffer. Enable. Same thing. Hmm. What are you doing? I'm making trying to make a 4-bit computer. I'm trying to make a binary counter here. I have a way of doing it, but I was trying to do a different method. Because here's the ALU. ALU. So we can select an instruction. One here is addition. So then we can give two numbers like 1 plus 2, 3. We get 3 as an output. We can do like 11 plus 2, 13. We can also select compare. So this prints out, well, gives a positive, gives 1 if it's the same, and if not, then it will just do none. So if we make them the same, we can see it's correct. And then we have AND, which is like bit mask. So basically if we put, say like this 6 here, you can see if we want this second digit, wait, sorry, we select, say, digit 1, so this one, it will tell us if it is a 1. So it's obviously not here. This position is not a 1, but if we select position 2, we'll see that it is. It's sort of confusing, but there's uses to it in modular arithmetic. And then all of this will come together with the RAM that I've made here. So we can select an address, say nibble 3. Nibble is 4 bits, so that's this register here. We can write, like, say 3 to that RAM, and it'll be stored there. And then we can select, say, register 2. We'll write like 6 to it. And then if we go back to register 3, you can see that it was 3, 2 is set to 6, and then the rest are just at 0. So then I'm going to make a CPU which can read instructions from here, hopefully, and then do computations with the ALU. What is it that I'm doing? I'm making a 4-bit computer. Yeah. But this right now is a counter, a binary counter. This is already a T though. That's what I don't get. Okay. This shouldn't be like the glitch. It should be alternating. So by using a 3-state buffer, ooh, the pulse isn't quick enough. Oh wait, I can change the pulse width. Okay, so let's put it back to 50. Now we can advance. Okay, it's triggering that, then they're both going on, and the NOT gate is then flipping it, which is turning it off. But because it takes a tick for the NOT gate to reverse it, maybe we can run the 3-state buffer off this. No, it would take a second. Server invite, like the Minecraft server. Yeah. It's not like it's Java edition. It's just my IP address. I'll put the. Hold up. Let me. Wait, I don't know if it's up right now. Hold on, I'll do that in a sec. How can this possibly? Wait, maybe this is what's broken. Because all that does is reset it. So we just need to send in the opposite signal once on the clock pulse. So a single pulse will then. Okay, hold on. A single pulse will send the opposite back to the set. Hold on. We need a toggle. Oh wait, server invite. Oh, sorry. Let me find it. I'm finding it, guys. Let me find it. Where is it? I know what it looks like. Alright, guys. Server. Moshi. What's that? Yeah, there's the, oh, sorry. It's off. There's the link. Moshi. Mosh. What's that? Moshi. I don't know what that is. How the frick do we toggle it? What if? Okay. Wait. We might be onto something here. Okay, so normally, right, the reset is here and it has a NOT gate, right? And this is like this, and it's just like that. So you, by resetting it, oh wait, hold up, that's wrong. That is wrong. Okay, let's build the same flip-flop sort of thing. So we set the value and then we reset, right? But what if instead of doing this, we sent in, if this here, right, was a 3-state buffer. I don't actually know if we need the NOT, so I'll just remove this. We might not. A 3-state buffer for the output of this, right? Wait, we could be onto something. Okay, so we can set the value. Oh. Oh, we might need the NOT gate. Okay. Okay, so it's high. So by setting it, the AND turns on. Right, and then by resetting it. But all we're doing. Wait. No, that's not good at all. Because all that's doing is just reversing the signal. We need it a pulse. How do we do that? Because this a pulse is all it needs to stay on. And you only need that to turn it off. Unless we're doing like this wrong. Or like that. Okay, what if we just put another one, like completely the same. Almost completely the same. Like an OR gate here. Only thing is, that, we have this be reversed. Maybe not there. Maybe we bring it to here, right? And then put this one here. That just makes it flash. Wait a minute. Maybe. I can't imagine it would be, but instead, if we take the not, wait, for the input line, from only NAND gates. We see a shift register. One bit register. One bit register. Never mind, never mind. Clocked flip flop. One bit register. No. Yes, like this. Okay. The value of 1 clocks that. Clock. Then wrong wrong one. Reset. So let's just reset everything. It goes straight away. Why does it go straight away? Unless we put it like this. So we have our value here. And then by sending this, we should, this button, we should clock to the next one. Okay. Why is this flashing? Why is reset line flashing? Oh, 'cause it's being powered by multiple. Okay, okay. Clock? No. Man, I was doing the same thing a few months ago. Really? Whoa. How far did you go? I cannot make for the life of me this freaking counter, binary counter. I swear I've made one before, but it's a pain. It's a pain. I'm trying to make like a shift register, right? So we clock this. No. Yes, like that. Okay, how about I make a delay circuit? So we have, all it will have is one input and one output. Alright. So right now the pulse just instantly goes on for a short time. Am I John Cena? No, but there was John Wiener was in the chat. He said hello. What? Okay, the pulse. We need, when this goes off, but it's always off. So it's just instant. Then what the freak do I do? I'm so confused. Okay, so we have the pulse, and then say we do like an AND gate between this and the output of the pulse. Wait, not the NAND gate. A NAND gate. Because that way... No. What am I doing? Oh, man. Okay, so we have a signal. If it's powered... Okay, so like a 1-bit register. For when this becomes powered. Okay, this is getting really complicated. But by setting this... The eyes just so we can see. So we set this, and then if the 1-bit register is on and this is an off, so then here's where we put our NAND. Oh wait, we're doing something. Okay, so let's just reset this. Okay, so by pulsing this, yes, that's where we get our NAND output. Okay. And now this will have like a delay of whatever the pulse is. So we can set it to 100. Oh, and then, oh, look at this. Then we can use that same signal to reset. But we'll just chuck one of these in with like a 50. Oh, and then we'll just have the same 56 for the output. Right. Let's make this one more visible. Okay, this is a nice use of the 1-bit register. But we have 2 pulses here, so obviously we can reduce that down. Okay. We're getting somewhere because now we have a way to delay. And if we go back to our toggle circuit, oh my god. No, clock flip-flop. No, that should be down here. Was it counter? If we had like some steps that we needed to do in order. So single copper bulb, man. How do we emulate that effect? Because like what if I put this, the output of this, wait, hold up. Let's see. What if this was just oh wait, that needs to be like that. Okay, so let's go back to counter. So like say this turns on. What is this? So shit, what am I doing? So when this turns on, when the clock signal is pressed, it will then go, it will delay and then it will reset, trigger a reset. But we only want to tap it once. Which is, I don't know what's happened here. It gets stuck there and then okay, so let's go through. So first, turns on, not switches the input. The delay circuit should be happening. Can we view? Yep, the pulse is still on. It's still on. It's like a 100 delay. Okay, so then it swaps. Triggers on. This should be triggering a reset, which should swap these. But that's not what's happening. Oh, I have no idea why. Why wouldn't it be happening? Oh, then it turns off. Oh, wait a second. Oh, because then we need another delay to then pulse the clock again. Okay, so let's wire this. There we go. Where is this going to? Okay, this will have an unpowered signal, so it won't interfere. Shit. We just need to reset it. Okay. Now. Oh. Bum. Reset. So I need to trigger it quick. Or I can set the pulse to just be like, to trigger both. I don't know why I didn't do it like this. Okay. Wait, it should be reset. What is happening now? These should be going on. Do we need to wait at a delay? Oh man. Oh man. This sucks. Like what the hell? This is the some fucked up. Hello, sup? Oh, can you please stop yapping and gaming hunter? Say hello, hello. Oh my god, I've just about had it with this one. Okay. We need a ripple counter from NAND gates. Because I had so many issues with these SR flip-flops, man. How about we see a video? This could be helpful.
Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the asynchronous counters, which is also known as the ripple counters. So in the previous video of the counter, we have seen that in the asynchronous counters, only one flip-flop receives the clock signal, and the output of that flip-flop is connected to the clock input of the next flip-flop. So in this type of counter, basically the output transition in the flip-flop acts as a clock signal for the next flip-flop. Counters binary is upcoming. Since it is a 2-bit counter, so we will require is the clock with clock. So they clock
Yeah, this all makes perfect sense, but we need the flip-flop. Flip-flop. Don't get striked. Oh yeah, it's music. I already have one strike. I think. Okay. Press the green button. Okay, what are R3 and R4? R1. These are resistors. We don't have resistors. This is just logic gates. Okay. Signal travels through the red wire. What? Do I have an OR gate? Is it just... Hello, Arixish. Hello. So it's just an OR with a NOT gate on the end. NOR implementation of a NOR gate. Why is it made out of NOR gates? You built a NOR gate out of... Are these supposed to be NANDs? Because that would make a XOR gate. No, using a NOR gate. Oh. Oh, this is a NAND, a XOR. What? Wait. NAND gate. And gate. Using, okay, yeah. Oh, okay. Universal. The AND and the NAND are universal. No, NAND and NOR. This is a NOR. This is a equal gate. Yes? Oh yeah. They must... There's a couple of them. It's not nice to watch. Okay. Or and a knot. Okay, this will be the NOR. Yeah. It is. Elton Siray, hello. Donna de Guzman, hello. I'm building a 4-bit computer. I'll be back though. Subscribe, thank you. This is a NOR gate, I believe. Or not. NOR. It's a universal gate, which means we can make any circuit from it. Wait, hold up. NOR. Oh. KL. Interesting. Okay, let's check. Okay, so only turn on if there's nothing. Interesting. That's interesting. Okay, so that's a NOR. And supposedly we can use this to make an SR latch. We have an SR latch, but it doesn't really work. But this is interesting here. So supposedly if we put two NORs with two inputs, we can connect them up like this. Riley Maudley, hello. How you doing? I'm making a 4-bit computer. I'm making a latch. We have a working ALU, which I can demonstrate. Okay, yeah, let's take a look at the ALU, because that's quite interesting. So here we can select what instruction we want. 1 is set to addition, 2 is set to compare, 3 is set to AND. So if we do 1, we can add 2 and say 4, and out here we get 6. That we can take a look at inside. We can see it takes the two inputs. Well, first it switches them to the signal, to the address we want, and we're using 1 for add. So it sends them into the add, and then say what we had 2 and 6, 2 and 4. It puts them into the adders. So straight away, hold on, 2 and 4. 2. Yeah, because it's a binary, it can just put this up here. None of them are on the same. Say if we had it like 6, right? You would see here that these two, when they're put together here, because they're both 1, it carries the 1 over, so we get a square lit up here, which is a 10. And then it all works together in the ALU. Like so. So say, let's try a comparison. So let's put in the number 4 and number 4, and we see 1, meaning true. If we put number 4 and number 1, it's going to be false. Then we can do things like bit masking. So say we have number 9, and we want to see, or say any number, and we want to see if, say this second digit, if it is 1. So we can select the second digit here, and we'll see it's on, so that means it's 1. If we put it on here, where it's off, we'll see it's off. So it works like that. What program is it? It's called Digital Logic Sim by Sebastian Lagui. You can find it here on itch. I'll put in the link, actually, because it's a nice program. They even have mobile version. Yeah, there, it's in the chat. And if you scroll up, the Discord is also in the chat. But yeah, this, you can do basically anything, make computers from scratch, which is quite interesting. And that's what I'm trying to do here. But I've made this SR latch, so we can, but it works sort of backwards. It's weird. We should be able to set and then reset, like so. And then these can be used to make binary counters, which is what I'm trying to do. But what I could do instead, which I might end up having to do, because I was having troubles with this, because we have the ALU here, we can just take the output of this and put it into, say, the input. So then if we add what are we doing? Oh, sorry. No, we take the ALU. It makes it very small. So we have input of 4, and we want that, and then so let's take the address, like so. Here, we'll wire it up. So we want to add, right? So that's number 1. Oh, it just started straight away. Sorry. So what we're doing is we're adding 1. I'll make it so you can see it. 1, and then the output of that is going to be 1, and then we're going to be adding it back into itself just continuously. And you can see it's counting up, getting to a full nibble, which is 4 bits, and then resetting each time. So that's pretty cool. You can just feed it back into itself and do all sorts of things with that. So here it'd be comparing for 0, and then it's outputting a 1, so it's sort of glitched there. But you can do all sorts of stuff with the ALU. Alright, I'll be back. Yeah, I'll be back in a minute. Oh, thank you. I forgot to turn my mic back on. What am I making? This here is going to become a 4-bit CPU. So this here's an ALU, and what we're doing is we're taking we're setting it to 1, which is add, and it's adding 1 to whatever the input, or adding this number, which is 1, to whatever the other input is, it's adding the two inputs, 1, and then the other input is the output. So it's just going to continuously add 1, and that's what's going up, and then it's resetting and just keeps doing that. And then what we're doing here is we're storing a number. Oh, let's reset that to this register, because see how this is just continuously on. We can make it more controlled, I guess, if instead we put the output into the register here. So let's put it here and rewire it up so it makes more sense. Okay, so we reset that. So right now it's outputting a 1 and it stores to there. Might as well just also put this pulsar here. It's just easier. Well, no, it's not really, but so there we have 1. So it's copying it there, and then we can then put this into here. Bro, I'm an idiot. Can't see a screen. Oh, I'm sorry, guys. So, this is an ALU that I made. It's not complete, but right now we're only using this first function here, which is addition. So it's adding in these two inputs. One of them is just 1. So whatever it's here, it adds 1 to it and outputs it. So right now it's 1 because the other input's 0. But then what we're doing is we're storing this. So now it's going to be stored. 1 is going here. And then we should be adding in again. So now it becomes 2. But I've just realized to store it, if I just store it here, it writes the bit on top of this. So I need to remove this and add in a second register. So 4-bit register stores just one number, 4-bit number. It's called a nibble, which is interesting. Wait, hold up. This is what I was trying to do before. No way. This could be... It's just a gate. Oh, man. Okay, well that's really good then. It's just a shift register. Cool. Okay. So we store the 1 there. Set it over 3. Okay, wait, it quickly gets filled up. So then we remove the reset from here. I'll need to automate these. But for now, let's reset both. Okay, so we transfer 1 to here. Transfers it to there. Now it's 2. We reset the first one. Store 2. Reset second one. Now it's 3. 3 stores. 4. Oh shit, I accidentally reset it. Okay, it's a bit clunky right now. 0000111. Wait, which tool? This here is called Digital Logic Simulator. Or Digital Logic Sim. It's called, yeah. You can find it on itch, made by Sebastian Larg. It's free. They even have a mobile version. And it's pretty good. 0000111. What's that? So yeah, the ALU. Let's go back to the ALU. Like, where is it? Here. It has multiple functions that I've built. So we've got the adder, which was what you're seeing. It just adds in the two inputs. It's like 2, 4, comes to 6. But we also have compare, which takes in two numbers again. 1 and 1, they're the same, so we're going to see a 1. But if I put two numbers that aren't the same, it's not going to be the same. And then we also have AND, which is used for bit masking. So say we have a number, we can detect whether specific ones are on or off. So we can see. Oh, sorry, AND. So we can see that this one is on and that one's off. 32 mouse bits. Mouse bits. Do you mean like a nibble? What? We also have RAM that I made here. Where is it? Let me find it. 16 nibble of RAM. So we can select that address, say like 6. So nibble 6. We'll set it to like 9. We can set that there. Oh, set. Wait, why is it not working? What's happened here? Oh! Oh damn. That's not good. It wasn't linked up past 5. Even though it's done. There's so many circuits. Okay. Let's go back to the RAM. Okay, so what we are setting, channel 6, we are setting it to 9. Okay, now it's set there, and then we can select a different address, say like 3, and let's set 3 to 1. Set that, and now we can go back to channel 6, and we can see it's still at 9. This uses the same 4-bit registers, just like heaps of them. With a switch to select different channels, and then these just select store and reset. It's just easier to use a 4 instead of single wires for cable management. Yeah, so that's basically that. I just need to make a CPU that combines the ALU and the RAM. But we might be into the clear with this one. Because I was having trouble with making a counter, but yeah, I didn't realize that this actually works. Like the shift registers. Like by sending it again, it could transfer it to the second register, and then that way, then we can reset the first. Remember the next number. Wait, hold on, what happened? Okay, remember the first, remember the second, reset the first. Okay. Oh. Oh, it got corrupted. Okay. Hold on. Let's step this back. So right now it's at 1. Save 1 to the first buffer. Save 1 to the second buffer. I might copy this over so we can see exactly what's on the second buffer. Alright. Second buffer is also at 1. Then we're going to clear the first buffer and then store onto it what was there. Oh, but that corrupts the second buffer. Okay, because now it has stored on what was there, which coincidentally didn't matter. Well, no, it set it to 3, which is the next number. But we should clear the second, transfer the first. Now it has 3. Now we can clear the second, transfer the first, clear the first. Now it has 4. The second then becomes corrupted. So I need like routines, subroutines kind of thing for transferring a number and then saving it. But yeah, this 4-bit register. I should be able to. Yeah, I should be able to make a shift register. I have to be able to. Because, like, it gets so convoluted so quickly. And what does ALU mean? ALU stands for Arithmetic Logic Unit. So basically, it's a circuit that performs okay. Let me demonstrate. So it just does calculations, basically. Simple calculations. Well, not really simple, but you know, so mine is probably, well, any ALU is going to be different, but mine it has addition, so it adds in 2 of these values. It has comparisons and then I'm going to add in some more for other functions. So it basically takes in 2 inputs and then gives you 1 output. And then the CPU will use this for any calculation. So I'll need to write binary and then machine code basically that the CPU will read, and then it will delegate tasks to multiple ALUs. Probably going to be easier just to have a single one at first. But it will say for multiply, the ALU could have a multiply circuit, or it could just add a bunch of times. Like, say 3 times 2, it's just 3 plus 3. Something like 3 times 4 is 3 plus 3 plus 3 plus 3. So we'll need to do loops in that. But like, the ALU is what does the calculations. It's a part of a CPU. But or it could be most of the CPU. Say something like a calculator that doesn't have, some calculators have like ROM, or no, it has bit of RAM. But say like a simple desktop, like say this, right? This is going to be just mainly an ALU with just a function here for storing into, like, say, like there's the little M, you can save some things, but mostly there's not RAM. There's just the RAM of the numbers that are on screen. If that makes sense. It's not a CPU, it's a integrated circuit. Which game is this? This is Digital Logic Simulator, or Sim. You can find it on itch. It's made by Sebastian Larg. I don't know how you pronounce it, but he's a YouTuber. It's a very good program. There's a mobile version as well. Yeah. What is it? 2 instructions. Wait, is it 2 inputs and an instruction? Yes. So this here is the the instruction basically. So 1 is addition, 2 is compare, so on. And then there's 2 inputs. I'm not sure how others do it. I'm kind of just like making it as I go along, so there's not much planning. But this shift register, right? So if I have a data and then store, so if I can then put in a I guess it would work like this, right? So the data goes in, and then the store button is just holding it there in the 3-state buffer. Well, there's not really a buffer. I don't know why. I suppose it is. So there we can, this would be data, this would be store, and then we'd have a reset here. But then I need a shift, which would then shift it down to this. So I would have another one of these here. A shift. Yeah, like this. Okay, so we take the output of this first shift register, and then we shift it like that. Okay, so shift register 1, register 2. Okay, so first we have our data and we want to store it, and then we can then shift it to the next one, which this shift will need to reset this line. Okay, so and then we'll have a this reset can also reset this one. Okay, so this is like a clear. Okay, data store shift. No, is this shift? Data store shift. Yes, reset. Oh man, this is working. Should I do the cable management? Nice. How are you going to command sequence? Command sequencing. I've never really thought of that. So that's where you have like instructions in the machine code, right? So I guess the CPU would just iterate through RAM. I guess I don't know how to define what areas of RAM. There's going to be so many like overflows. You'll start reading from the wrong spot. This simulator has inbuilt ROM, I think. This 256 by 16. I don't know how this works. 'Cause 16-bit, I guess. And I don't know how you would write anything to this ROM. I guess probably in the project folder. I might make a Python script that will just have things on or off, so shouldn't have to worry about that. Until what I'm trying to say is, yeah, I'll make a script so I can then write data directly into my own ROM chip when I'm up to that. Command sequencing, I don't know. That's going to be difficult. Everything is going to be difficult. I've only just made a shift register and it's very rudimentary. Well, I mean, I could do... Okay, reset, right, shift, reset, right, shift. Oh, this is an issue. It doesn't shift in zeros. I wonder why that is. Because we definitely need that. Why would it not be doing that? 'cause these. Oh, 'cause it's the 1-bit registers is an SR latch. I thought he was a cowper. Yesterday someone said the exact same thing. Is that a compliment or is that? I don't even know. Yeah, I guess we want it to shift in zeros. Wait, what? What the hell is happening now? Sometimes just pressing shift just blips it out of existence. Oh, 'cause shift it resets the first one. Hmm. But if we're not shifting in zeros, then I mean, should I just? This is currently 2 bits. I guess I'll just make it. Wait, this is shift, right? Okay. I guess I'll just make it 4 bits and then we'll see what happens. So you just need to output the last one in, and then all shift does is just transfer it. And these reset pins will just be connected to the reset. Okay, so we should be able to write there shift O. What happened to it? Maybe I'll. Wait, shift should really be the same thing as this, shouldn't it? Okay, so data, shift, O. Oh man, what the hell is that? Sorry, but more complicated. But sorry, more complicated. Command plus plus. I am so confused. Like, why did they all turn on? 'Cause okay, so we should. I guess they're just like all triggering at once. Okay. They must. We need some like delay between them, I suppose. No data there. I mean, I have a delay. I don't know how well it works. I haven't maintenanced it in a while. Okay, so the delay will then. Where does this connect to? Shift is the bottom one. Okay, and then it will also connect to this delay, which will then enable that. Okay, so we'll write to the first bit. Oh, look at that. Yeah, it was what was happening. So it writes it, and then it's just chain going down. Do I need to? Maybe, wait, hold on. Maybe I go the other way. Wait a second. Okay, so on the first, get back. Okay, so the first one, yeah, I don't know. Okay, so straight away, we'll just power this bottom one. And then it will also go into the delay, which will then power this one, and then that will do that. Okay. in save to the first. This is way too tangled. I need to, well, let's just remove all the delays and everything coming off the shift register. Okay, let's make it nice and neat. What are these connecting to? Just to the reset pins. Okay. I'm gonna. Okay, now now we know what we're doing. I'll just label these. Now we just have the laborious process. We just need them. Yeah, I'll just put it on the line because that's better. Alright, yeah, this make it look nice. Okay, 4 bits. Data in will be here. And then, okay, so what we'll do. Oh, Matt Thompson, happy birthday. Happy birthday. Okay, let's connect the rest of the reset pins. Why is that like that? We want it to be there, there, there. Reset, and then the final reset pin. Oh, this is nice. I'm liking this. Everything's going good. Look at that. Reset. Yes, that's nice. Okay, in. And now we want to shift it from the bottom. So I'll use delays. I feel like if you had... I don't know. In this, I'm trying to think like whether in real life you need it. You probably would. You would, right? Unless we got the output of... Never mind. Let's just take the delay. No, hold on. The first one. Okay, so this will be then, say we just connected this up here. Okay, so that's on. Then, oh, wrong one. This is the output. Oh man, then, no, we're gonna have to move it. Oh, that's heartbreaking. No, hold on, it's alright. Because we can just, yeah, look at that. Look at that. Everything is working good. Oh man. This is something to be happy about. Oh, I forgot to select those. No, it just deselected. And then we just select all the... Oh, look at that. That is beautiful. That's amazing. We'll put all the reset ones down here. Chuck the shift button there. Data in, we'll just make it lined up. Oh, I'm so happy. Happy birthday, Matt Thompson. Okay, reset. We'll just set this one live for now. And then what we'll do, we'll bring this down. And this is going to come along through here into the in channel. Right. Maybe we can... Yeah, okay. And then shift will be the enable. So that, oh, look at that. It copies it over. but shift is gonna enable everything. Oh, hold on. Okay, let's remove them for now. Because this one here will be wired up. And then, oh, but it's not copying 0. It isn't copying 0. That's an issue. Okay, let you see it come a second later. Let's think about this. Well, we could just reset it. Yeah. Wait, we need to do that. Do you like cassette players? Yeah, I have two. One's a mini tape player. They're pretty cool. You know, magnetic stuff. I mean, yeah, I was looking for one a while ago, like a Walkman, but they're so overpriced, you know. But they're cool. I like old things. Okay, so reset and then read. Oh, look how smooth that is. Ooh. You know what? I think I might. Okay. Pack a bunch of delays in a separate chip, right? So let's put. We'll have a single input, and then it will just run up the line. Because these delays are going to be useful for timing. Command timing. Which is very nice. So let's chuck these in. And each one, it should straight away work. Oh, look at that. That's perfect. Ah, that's perfect. Delay. 4 delays. We'll just call it 4 delay. Yeah, that's very nice. Let's go back to our shift. So for the first one, we want to trigger the reset, and then the great reset. Oh, look at how it runs up the line. No, hold on. Hey. First, actually, we want to trigger this one. Well, I'm gonna need 2 of these 4 delays, because the first one, it could happen instantly, but we need to reset it first anyway, so we might as well do that. It's nicer. And then it will trigger this, and then it will trigger this. Oh. No, hold on, this could be worse. Because then we need another delay here for then this to be triggered. And then this to be triggered. And then this to be triggered. And then this to be triggered, but it needs another delay. So then we're using up that. And then that. And then that. Oh. Okay, it runs up though. Look at that. As it runs up the middle. Hi. Kayla Q2M1U. Oh damn, you know, that's the problem these days. All these names are being taken like, you know, I go by Indo to Pro, but like that's what I was thinking, like within a couple years, how's anyone gonna make a username? We've got billions of people. I guess most people will be dead at a certain point. Like apparently most Facebook accounts will be like quite literally ghost accounts. So yeah. That's a weird thing. Oh no, something's wrong. Oh no, look. It doesn't shift it. Oh, I see. It's just not connected. Don't worry, it's just a little problem there. It's not a big one. Oh, that's beautiful. That's beautiful. Big brain stuff. Well, it's you know, it's simple. It's not. It's it's simple stuff, just a lot of it. It's too tangled. Should I make it clean? It's gonna take so long to make all the wires clean, but you know. Okay, wait, we have 1, 2, 3, 4, 5, 6, 7, 8. I might as well make an 8 delay. And rather than using the 4 delays, because you need one more to chain it through, so if that makes any sense, I'll do it like this. Oh wait, hold on, no, you don't. You can trigger 2 things because it will. You could do it like this. Yeah, I'm making a 4-bit computer if you just joined. Yeah, you could do that and then have the output as well. Oh well, I'll just do it like this because it's, well, I was gonna say simple. It's more complex, but it's, I don't know. So yeah, this 4-bit computer, 4-bit computing is completely useless these days. But it's good because you can almost understand, like 32-bit CPU, that's just way beyond. You can't even comprehend, like, well, I mean, you can to a degree, but the amount of, it's just too complex. It's nice to be able to see and make by hand. Well, not really by hand, but you know, it's nice to be able to see every bit of it come together in a way that's manageable to some degree. Look at that. Oh, we got the delays. 8. Oh, 8 delay. Digital Logic Sim. Yes, that is the one. You can find it here. Oh, wait. Oh. Oh, wait. Oh, thank you. Thank you for answering the question. Yes, Digital Logic Sim. It's on itch. I'll post again the into the chat so you guys can see. And I'll also put on the Discord link. You know, this is one of a very successful stream in my opinion. We've got nice discussions happening. So yeah, check the Discord. There's a lot. Well, there's not. I said there's a lot. There's nothing in there. There's a few people, but join up and then we can start a community really. Wait, why did? Interesting. Okay, this 8 delay, but first I will fix up these reset lines. But the shift needs to trigger a reset, so while we're here, you know, we might as well bump everything up by 1, because that way that'll give us. Oh, we need to use this. Okay. We need both ends of the wire. I mean, that's fine. Okay. Yeah, that's alright. I don't mind that. Let's. Oh. No, because what we can do is we can just bring our reset line back here. Because the resets are instantaneous. Well, theoretically. Oh. Oh. No, that's not good. We'll just take the whole thing and bump it up. Wait, that's not gonna work, is it? Because we want it to be on the line, just for organization's sake. OCD. No, I don't have OCD, but it just makes readability better, you know? Because we want to be able to come back and actually understand. And I want you guys to be able to understand because it's a learning. You know? That's the purpose. Okay, we can go and delete that. We can delete this. And then for these ones, cause one's an input. It's fine, we can just delete that. Sometimes you can join the wires and delete the other half, but for whatever reason, well, not in this circumstance. Okay, so now we have in, and then shift. Oh man, this is becoming a nice clean circuit. I'll just need, that's weird. Really the first delay. The first delay here will go out. And trigger this. So that's sad. That doesn't line up perfectly. Okay, the first one here. Oh, this is missing something. Oh, it's missing the, hold on, let's put this in first. We're missing the reset line for this one. So we can just go here and should be top one. Yeah. Alright, I'll put this here. So this is the shift, goes through the tower delay. We'll chuck that there. So firstly, it'll come down. Yeah, like right here. Look at that. TS looks tough. Tri-state buffer. Oh yes, sorry. These are 3-state buffers, which I don't know why they're called that, because it's just a transistor. You have in and then enable. Hardra. Tri-state buffers. Yes. This looks weird. Maybe I should put it like. I don't know if that looks better. I guess I'll do them like that. Equally unlegible. Legibility of code and then wiring. It's interesting. It's similar to language in a lot of ways. Computing. Well. Oh, look at that. Perfect. Okay, so say we have data here. Oh man, look at that. That ripple effect. Oh, that's beautiful. And so say we have it like this. We'll just... Okay, it's a little slow. But that is not bad at all. Hold on now. I'm just thinking. Surely we couldn't have done them all at once, right? I love your hair and voice. Thank you. If we'd done them all at once, would that have worked? I don't know what would happen actually if we did them all at once. Because then they would all be copying from the one above. Yeah, it's probably best to add a delay because otherwise, because the top one's changing, so it could just end up being random data. But what we can do is we can open this and we can, yeah, look at that. We can fix the delay here to have, say, like 50 pulse width. It's still like after, but then that will just really make it much faster, or twice as fast. Because when you have 8 delays stacked up, you really notice it. But Yeah, that's nice. And because, oh yes, because we're resetting it each time. Oh, this is one of the more simple, but more cool looking ones. Oh, wait. Hold up. If our clock was faster, we would be having 2 shifts at once. And I mean, that's not good, but it could work as well. Oh, what's happened here? Oh, never mind. I was just highlighted on it. Okay, so look at that. Oh, that's incredible. Oh, I like that a lot. What game? This is Digital Logic Sim. I'm building a 4-bit computer. You can find it here. It's made by Sebastian Larg. And like and subscribe to follow along with the series, because hopefully I'll end up building this computer using the same logic out of Lego. That's the idea, because Lego, like, you can use binary basic, like, logic gates. You can make them out of not just using electricity. It's quite incredible. I could just bring these down. Yeah, look at that. Then we have more all straight lines. It's nicer. Someone's spamming likes. Oh, we can get rid of that one. Okay. Yeah, that's nice. We now have our shift register working. We'll call this one data. Okay, now we just need our let me think. We can probably use the shift register for a binary counter. Or maybe a 1-bit or 2-bit shift register. Because if we think about it, if we have on, okay. We need to do an operation onto it. I'm trying to think, because do you like horror games? No, not particularly. I mean, although I haven't played any. Well, some, like, on very occasions. Someone is still spamming likes. What do you guys reckon? Is this possible? Because I feel like at one point all I needed was a shifter to get it to work. Because if rather than just shifting it, we could do a computation. So it's gonna be like a sort of hardwired addition circuit. Yo, movie recaps. Hello. How you doing? I'm making a 4-bit CPU right here. And this is a shift register. Look at this. Is that not incredible? I'm very proud of this one. How it runs up. Because this is multiplying by 2 if we think about it. Okay, let's... Ooh, yeah, it is wait a minute. What did I call it? Shift? Yeah. Okay. 1 to 4. Hold up. Look at this. Because all this shift register does is kind of multiply by 2. Okay. Let's just chuck these in. Yeah, okay. New step to our ALU. Okay, so say we have... Oh. It's gonna be up top. Should have... Okay, we just reverse it. Okay. So 1, 2 times 2 is 4, 8, 16 is it resets. Well, this is multiply 2 plus 1. Wait, 2 to... Oh no, it's in binary, so it doesn't quite work. But, so we can multiply 2 once, twice, 3 times. And then after that, I guess you just need... It just overflows. That's the problem with 4-bit. Hey, give me $10. $10 from my card. No. I don't have $10 in my card. But it also works for other numbers, right? Like say 3, 6, 12. Oh, and then it overflows, and then you just... Okay, I think this is worthy of the ALU, you know. 4 to 1. Okay, it's not bad. 1, 2, oops, 3. Okay. In 4. Yeah, so if we do it let's do it like this. So unsigned integer. Wait, will it work for signed? It should do, right? -6. Oh, wait. Never mind, we have to manually program it in. Okay. No, not for signed. Or it overflows into negatives. In this case, ooh. Yeah, no, I mean, we can do double. I mean, we can open up the shift register and instead, we could put on all of these lanes, like I mean, we could put data in here. Yeah, say we do in 4 and then 4 to 1. Okay, so we're gonna be taking this value and then yeah, like that. Look at this. Okay, I mean we can reset and then and then we can like shift that up. I mean, I can do like, I could add in a store. And this is kind of like hijacking some of these lanes. So we can, why does that? Oh, it's got issues. Oh, so I guess you just have to manually, you just have to shift it and then it will just chuck it in. Okay, so we don't need store. So running, so we can call this one data, and then we'll call it in. Okay, so then by making the double can then, instead of that, use this, and then, oh wait, hold on, we still need it for this, so okay, well it kind of should work. It should kind of work. So we can then what am I doing? 6, and then we can then double it. It's not that. Oh, and then you have to remove the data, because then it will add it back on 12. And okay, that makes sense. If we have like 14, yeah, that makes sense, because that's 12. And okay, the double works. Oh, there's been a lot of chat. Also, use JavaScript. Heck yeah. I learned some basic JavaScript back in like last year. Have you designed Gabe Owner's Gate? What's Gabe Owner's Gate? Console.log. Hello. No, it's log console.log, not log.console. And then yeah, you've got the this thing at the end. That's important. What is Gabe Owner's Gate? Let's have a look at this. Yeah, console.log would be for, yeah. What the hell is this? Gabe Owners, I don't know. Log. Give me $10, I'll give you 1,000. What is this guy on about in the chat? You can use Gabe Owners. Is a strange guy by the looks of it. Okay, let's see. Let's go back to our ALU and let's add in the double command. It's going to be quite specific. I mean, there'll be definitely cases for it, so I think it deserves a spot here. And then Oops. Listen to what you're saying. He said Gabe owners. What? Gabe owners gate. That's what he said, right? Gabe owners. Gabe. What? It's Gabe. Like Gabe Newell, but. What the hell? Frick you guys. I thought it was like Gabe Newell. I'm not saying it fast. What the hell? Who is this guy? I'm banning this guy. John Madden. That's all you had to say. I hadn't heard of that one before. Okay, double. Wait, there's kind of no point in this. I mean, it's weird. It's dubious. It just glitches out. Why? Who wants this? Gabe owner. It's like this weird AI thing as well. To oh wait, 'cause it has registers in it. Hold up. Wait a minute. This is not compatible with an ALU. An ALU, let's look at the definition of it. It's meant to be, it does arithmetic bitwise operands. It's meant to be like single state. Like you're not meant to be able to. It's not meant to have RAM in it. So by doing this, by using this shift register, we could like corrupt things because we're not supposed to. Like you would put something in and the shift register would already have stuff in it. I think. What am I thinking? That's it. It doesn't work inside the ALU. Because it would lead to issues. Like we can store, what, 2? Why is it storing 4? I'm still mad about gay boners. Why is it storing 10? See, look, this is the... There's no reason for it to be doing this. Okay, 1, 2, oh, 1, 3, okay. 1, 3, 7. 2, why is it storing 2? No way, it's like inverted, right? Yeah, it's... This is some bullshit. How did I not check this? Oh. Wait. 1, reset, 8. Freaking, what's his name? John Madden. He probably goes around all sorts of. He just goes around just getting people to say that. I bet that's what he does. He knew enough to know it was a gate. And that's all he said. Where's the double? We want it to add it to stars. Starred. Okay. So let's say 6. 6. Okay. Yeah, it doesn't like. It's not gonna be good in a ALU. 2. 6. I mean, like we could just, just reset it. But then you have to resetting it each time. And yeah, because the CPU could delegate tasks to a different ALU that doesn't have it stored. Building what? A computer. A 4-bit computer from scratch. Out of logic gates. Yeah, this double is not what we want. I mean, there's got to be a way to do it without. How would we do it without? I mean, we could have a 4-bit register that just self-resets. No. No, I feel like that's not gonna work. We could just have it hooked up, like wired directly. Yeah, 'cause now I want to do a double, 'cause we've made a weird one. Yeah, why don't we do it? In 4, out 4. If you guys have any suggestions of what I should make, like some other guy yesterday was saying I should make RAM, and I did. Not that I've used it yet, but it helps to have like stuff, 'cause then you can piece it together. Okay, this should multiply things by 4. No, by 2. What am I saying? By 2. Oh yeah, it'll just shift it up. It's a very simple sort of thing, because really we have 1 that's gonna be this. We just need it like. Oh, what happened? Oh, yes. Wait, 1 becomes 2. Okay, and then because we can't have that second. For fun, yeah, pretty much. I'm gonna try build it. Oh, we got 21 people. That's crazy. I mean, you could put it like this, so that way. 2, 4, 4, 8, 8, 1. That's 16. I mean, if we made it signed integer. Oh, it's also 1. Yeah. Rustic core. Oh yeah, I think she is. 3. Yeah. Maybe we don't need to carry this second. Which software is this? This is called Digital Logic Sim by Sebastian Larg. You can find it here on itch. There, I've put the link in the chat. I'll put it in again. There's even a mobile version that you can find. It's pretty nice. But yeah, this here should just double whatever we put into it. Da, da, da. How would I do it? Because it carries over, so I guess we can do. Oh, like that. Where'd it go? Oh, it's down here. That's weird. No. Oh, here it is. We'll save that. There. And what's this? Is this the same thing? That's weird. Oh, wait, you can duplicate things like that. Oh, that's crazy. I didn't know about that. Yeah, I guess we'll just do a overflow. We probably won't use it. Well, we won't use it in the ALU because the ALU only has one output. But we can, so that way if we get 8, they'll light up 16, and then we can do larger numbers. Yeah, that's nice. This is what we're gonna put into the ALU, if I can find it. Where's the ALU? Where's the ALU? It's quite the way back. Any chat? My friend Dinglin, my friend Danglin Dong. Shout out to Danglin Dong. You monkeys. Gabe. Yeah, shout out to Danglin Dong. Who says that? Who says that? You're supposed to be a moderator. You're supposed to be helping. Alright, see ya. I'm tired. Okay. Alright. Yosh. You're helping Dom. Alright. See you guys. Okay. What do I make? Chat. I need your help. What do I make next? There's 14 of you guys. One of you can surely say something. And not Dangling Dong or freaking gay bonus. I can't believe this. I can't believe this. And then, okay. Fine. You're not gonna say anything. I'll just do it myself. We need to make a counter. How do I make a counter? Frick, this has been like... Okay, count up. when it's 1 and we receive the shift. If it's 1 and we shift it down, then set next one to 1, right? So like we're shifting up. Cool stuff, good lunch. Hello. Oh my god. DK Gaming. Mango leaf tea. Cool stuff, good lunch. Getting it. Good luck getting it working. Oh, thank you. I need to make a counter right now. This is a 4-bit computer, by the way. This is the an ALU, arithmetic logic unit, that will be in the CPU. Just recently made this double, so we can put in like number 6. Oh, wrong input. We'll call this one A. So yeah, we get 12 out, because 12 is double 6, double 7, 14. You can do anything up to 14 bits, but obviously once you hit 8, or even like 7, no, it can do 7. Once you do 8, it will overflow, so we'd be getting a signal out of here, but we only have 1 nibble, which is 4 bits. Let's check chat. I was wondering how to get the bus working. Oh, the bus. They're eyeing Australia. Wait, sorry, let me just check back through the chat. Oh wait, mango leaf tea, yeah. Here. Mango leaf, sorry. Why did I say tea? How to get bus working. Wait, are you using the same simulator? Basically, let me do a demonstration of the bus. So if we do a single bus, right? I like to flip them so they're the same way, because then you can do it like that. So right this is a bus lane. You can have an input like that and an output like that, and you can put things onto the bus. There's one little issue. this fucking thing. Which is a problem with the simulator itself. Oh, no way, Lebanon? Oh no, is this the Ghoulie edits? No, it's Lebanon guy again. No. No, there's no way. How did you find me? How did you find me again? Oh shit, he's posted more videos. I remember you. Don't think I've forgotten. Australia soon, Lebanon. What are you on about? You're an insane person. This guy, this is a strange guy. Okay. Yeah, basically you put stuff onto the bus, but because we have an off, this is technically off. It gets really weird. And then basically you just yesterday I was talking about how I hate basically, and I keep saying it. You need 3 state buffers, because when I don't know why it wouldn't just be off. It's like dark, so it's like it's not powered. It's not a 1, it's a 0, but it's not off. But off can also be used as 0, because if you just do it like this, right, then that goes onto the bus, that goes onto the bus. It all works happily. You can power them both, obviously. Yeah, it's a strange glitch. Oh my god, we've got 21 people. 1.3k total. Oh, what do you mean find it? You're a subscriber? How do you make RAM? Oh, Anime Glory. Hello. Sorry. I'm just struggling to keep up with this chat. The RAM. I made RAM here. This is 16 nibble of RAM. So nibble is 4 bits. So what we do is we select our address here, and it goes through into this switch, right? 4-bit switch. So it's a massive switch, and it also goes to this switch. So this is the input switch. So then when we put a number, say 6, right? It connects us up, 6 here. It only allows it out this port into this 4-bit register, and it also hooks up this other port. This is for the data here, channel A, to go into the 4-bit register, and this is for the button. So we have store and reset. So that allows us to store to a specific nibble of RAM. Set and then reset. So then we can select a different address. But notice how, see, this is on, because if we connect anything, set different numbers in any, they'll just be on. So then we have our second stage switch over here, which allows the output. So it takes in the address, and then it only allows the output of whichever RAM slot we're selecting. That's the basis of it. Yeah. He's making a motherboard. Yes, I'm making a CPU. Basically, motherboard connects the CPU to the RAM, but it will have integrated RAM. And then my plan for this is I'll build this CPU, but using probably Lego gears, because you can actually simulate logic gates with not just electricity. So that's an interesting thing. But maybe I'll be able to use this same architecture once I get a test working. So yeah, I hope this bus helped, because it just allows you to power multiple. Wait, hold up. Let me actually see. I do have an example of a bus somewhere. I used it somewhere. Maybe in our decoder. Yeah, in the decoder I definitely used it. So here we have 8 buses. And you can see when we have a number, how it basically works is we have always 4 of them are on, 4 of them are off, and because 4 of them are on, we can manually go through and say when you have a binary 3, there'll be these specific 4 on, and then we can use the AND gate to turn on a number 3. So rather than having like thousands of different wires all connecting to each different AND gate here, we can put them all onto the bus, make it super simple and easy. Looks nice as well. 20s. What are you doing here that you can physically build? So all these is simulating an on or an off, right? So it could be electricity flowing through this wire, that could be an on, and then this, you have basically logic gates. So a NOT here, all it does is reverse the signal. So if it's off, it's going to be on, and if it's on, it will output off, and if it's off, it will output on. But on and off could be whether an axle is spinning or a gear is spinning or not. And you can simulate, like here, this logic gate is made out of a NAND gate, but you can make all NANDs are universal gates, so we use them because you can make anything out of a NAND gate. But you can do the same thing with anything, really. How does it work? What? That made no sense. It's confusing. But it's fairly simple. Anyway, it's not. Every step is simple, but there's just so much going on, and it's hard for me to explain it because I don't fully understand it either. How does it work? Like this here, this specific thing works by putting in a number in binary. So binary, you have ones and zeros, but on or off is also the same thing. And this here is decoding it. Anyway, this is just a view to see. Makes things easier for me. But say 4, 0, 0, 1. But what we're doing, because the computer can't see this, so this is manually finding out that it's a 4. Because say when it's all off, all the NOTs will be on, because their inputs are all 0, so their outputs are all 1. But when we turn on 1, then it flips it from being off to on, but we still have 4 lit up. So when these specific combinations of ons are on, the AND gate, because all of them have to be on, this and this and this and this, once they're all on, it will light up, telling you it's 1. And then I've used this decoder in this switch. Yeah, it gets even bigger. So this switch here, it's this decoder, sorry, is telling it the address. Mechanism of this logic is most useful where? This is how every computer works. on the most basic level. So if you look at a silicon wafer that a CPU is made out of, central processing unit, it's going to be tiny transistors, and transistors are what make up all of this. All the logic gates are just layered on top of, not on top of each other, but they work together. Okay, what program is this? This program is called Digital Logic Sim. I've placed the link in the chat a couple times. It's made by Sebastian Larg. You can get it on itch.io. So basically, what this decoder does, right? We put in a binary number, and it gives out a different lane. So here's a different number here. So if we select address 1, it will power this gate. This is basically a transistor. So when it's on, it will allow data to flow from this address to here and from this address to here. So by inputting data through one of these two addresses, right? We just put 3 and 5. It allows it to flow here and here. So this is 3 and this is 5, and then the rest are all off, because if we have multiple on, then, well, it would go badly. So then if we look inside the ALU, sorry, I'm trying to find it. Where is it? Somewhere here. Yeah. So this you use as a switch. So here's the data that we're inputting in, and then here's the address that we're selecting, right? So we're selecting this specific one. For this, we're using addition. So it allows the data to go into the addition circuit, and the 2 that we're using is for the 2 numbers that we're adding together and then putting out back into this other switch, because see how this compare. What this does, it compares if 2 numbers are equal, and because they're both off, they're both equal. So if we didn't have the switch, they would both be putting information out, and then it would just get corrupted. So this, we make sure by using the same setup, very similar setup anyway, we're making sure that we only see the data that we want to see. So we've selected here address 1, which is addition. So we're getting address 1, and it's only powering this gate. Let me see. Yeah, see, we're getting information on address 2 and address 3, but we don't want that. We're only powering this gate, so we're only seeing this is a bus here. They're all connected to the bus. We're only seeing address 1. And that's how it works, basically. We can select compare, and now it's comparing 1 and 1, and it puts out a 1, which a lot of the time means true, or it can be an actual 1. We can do bit masking or and, which is also going to do a 1 in this circumstance. If something like this, it would be a 0. I don't have a use for this yet, but we can also do doubling. So this circuit, all it does is shift the binary data 1 place over. This is very simple here. It's just shifting it into the next space. And because of how binary works, that multiplies it by 2. So 1 is going to become 2. We don't even need this because it only uses 1 number. 2 will become 4. 3 becomes 6. That's how it works. Oh my god, there's so many chat. Hold on, let me read the chat. What program is that? Sorry. It's Digital Logic Sim. Again. My question is, what are you gonna build that PC in? Wait, my question is, do you gonna build that PC in the future without buying PC components like RAM, motherboard? Well, I already. It's not gonna work like an actual PC. Like that. The amount of transistors, the amount of stuff they pack into it is actually insane. So like, I have a PC, but this design will be like my own custom design that it's more just like, it's like as a demonstration, I guess, to understand how a computer works rather than actually using it. But maybe. You're welcome. Are you an IT student? No, I mean like, I'm on holidays right now, but I'll be doing computer science next year. But yeah, I probably will. I'd want to do that for like university, something along this lines. If you make RAM, then is it the most expensive? Like actual RAM, same thing. It needs to fit so many transistors into the one space. It's crazy, and we have very few like actual source manufacturers that produce the actual chips. There's a lot of companies like Corsair, that make RAM, but they don't actually make the chips themselves. They come from TSMC. They come from who gets the machines from ASML, and it's a very big monopoly. So we have very little source producers of the RAM, and then we've got massive AI data centers buying it all up. Same with other components and graphics cards, although they are now buying specific like NPUs. So graphics cards have gotten slightly cheaper, but it's insane because of the AI bubble. All these companies overvalued. They have so much money. They're just putting it all into AI, and then the consumers get the rough end of the stick. Get nothing. So that's the RAM shortage explained. Yeah, it's crazy. Do you think the project can change something in community? I think that project can change something in community development. No, it's not like anything groundbreaking. This stuff here has already been like invented like years ago, like 30 years ago. But I'm rebuilding it from scratch with my own designs, so it will hopefully help me understand and explain it to other people. As it's a cool project in my opinion. Have you played Turing Complete? No, a Turing machine. No, I haven't heard of that specific one, but Turing machine is a very simple computer that can be programmed to do pretty much everything. Why can I see 3, 4, 5, 6? PC only had binary numbers 1, 0, and 1. That's what a decoder does. It turns a binary number into normal numbers. So, if we go back to our decoder, where is this? Sorry, let me find it. It's somewhere here. Where is it? Oh, I saw it. There's a lot. Okay, so these are just labels for me to see, but they're different lanes. So it's powering a different one based on a different number here. It's not the logic gates only handle 0 and 1 on or off, but it can trigger different logic gates based on which ones are turned on. Turing Complete. No, yeah. Building your own computer out of NAND gates. And your own assembly language. Yeah, so that's basically what this is. It started with a NAND gate. Maybe I'll look that up because it doesn't have a good way of importing in like codes. It would be quite difficult to write programs onto this because you can't really save to disk directly. But hopefully, once I sort of design the architecture, because I've started on this already, then I'll see about building it and maybe in another program. Yeah. So what was I doing? Double SR latch counter. So I want to make a counter. And I think using, oh yeah, it's such a mess. I think using the shift registers are going to be a good way of doing that. Yeah. When is your design? Sorry. When if your own design, it's powerful or not? Do you mean like it's gonna be? It's pretty much impossible for me to make it as powerful as like a consumer product. Well, one because it's being simulated, but also you got like heaps of people working on it. I'm just doing a very simple rudimentary thing. I just like a calculator. I'm basically making a calculator. Hi chat, hello, Audriana. Okay, I'm pretty sure shift register is what I need to build. I've built one already, but a different sort of shift register, I think. Although maybe I can use the one I made. Sorry, it's so hard to find stuff in here. Okay, so let's take. So we want an input, right? So this, and then once we pulse the clock, let's grab some outputs. Okay, so so it will put it there, right? And then once we trigger it again, it will move it down the line. So that's what shift register does. It transfers things across. So is there more chat? Hello. Why build your own design? Because it's interesting to see how it works from the ground up. Because like, you know, you can, if you learn like a programming language, you can build things for a computer. But it's good to have an understanding of the hardware completely. And then also, I'm gonna make some more videos about it, so then to explain it to other people. Alright, let's see. Shift and then, but once it gets here, if this is on, we need a AND gate. So if this one is triggered and this one is triggered, and then suppose we shift that. I'm gonna have to think about this. I'm gonna have to use a lot of gates. We can use a NAND with this, so if one of them's on, then we data, and then we'll add in our delay. Yeah, delay circuit. Oh, not that many delays. And then we'll shift this, but I need also a reset. It's very hard to see what's happening, I know, at the moment, but I just sort of need to do it, and then I can work out the wiring to make it better. What? Can you play Fashion by Cordis? You mean like, is this a song? Because I already got copyrighted. I was just watching YouTube shorts on the stream. I'm sorry, I can't. I'll get in trouble. New video games. Wait, do you believe that new video games can play on low-end potato? Yes, yes. This is what I was talking about yesterday. Because like, so many programs are so inefficient. Like, we've got so many frameworks stacked on top of each other. Like, it makes things easier to program, but in the long run, then we just need more compute power stacked in together. We need more and more transistors. That's why we have Moore's law. We need to be constantly increasing, and things get more and more inefficient when a lot of the time, if people took extra time to optimize things properly, we could run it on much lower end devices. It would be a lot cheaper for the consumer. So that's what I would like to do when I'm making my games. I tried making a 3D rendering engine. That didn't work too good, but it didn't end out very well. But you know, there's a lot of optimization. Yes, it's a good thing that we need. Okay, so oh. What happened there? This one got triggered. Uh, and then we need. Okay, I need to make this sort of be able to link as many of them together, but that's difficult. Yeah. I'm trying to think how we can get this to work. Wait a second. Okay, so let's open up this shift. Well, let's save this here. Open this one up, and we have this shift register in here. I'll make a new save. Oh, no, not like that. No, open. What am I doing? Okay, we'll save. We'll do 2-bit shift. Hold up. No, we can call it toggle, because I was trying to make flip. whatever. I was trying to make a toggle before, but I realize now that shift registers are probably a really good way to do that. If developers optimize games for low-end devices, they lose many players. But why would they lose players? Because it's not like if you have a more powerful PC, it's not gonna run worse. It takes more money, so companies don't want to do that. EA is a very good example. They just want to get games out, and they don't focus on making them putting any effort into them. If games were more optimized, it wouldn't make things. They wouldn't lose players. They would gain players. Okay, so this ripple counter. I should. Okay, I've made a copy anyway, I think. Okay, I should just be able to remove these top two, right, and then have the into this. Wait, how do I do that? Oops. Oh, what's happened? That's weird. How can I just delete all of them? Oh, that worked. Wait, but then what was... Oh, okay. In shift. Okay. Now once I shift this, instead of going down, we can make it trigger... No. Because this one, it's connected up to the input. Why isn't this working? It should be shifting. This one here should be copying from that. And I don't know why it isn't. Is it this causing an issue? I think it was. But I don't know why it would be. Okay. Reset. Now, where did that data come from? Oh, because it's in. This is interesting. I'm not sure what's happening here. They lose? Yeah, they wouldn't. I'm not sure what you mean by that, because, yeah, by making your audience wider, it's beneficial for everyone. The thing here is we're not triggering a swap, but I don't know why. Like, okay, that triggers there. It moves on. Yeah, that's good. Okay, now this one. Oh, I think I get it. Because at first we're copying to this. So we need another one of these. I mean, I guess if I just added these back here. Okay, reset. Oh, I'm not. Okay, there. So the first one goes here. We remove that. But then why? Okay, how about if instead of getting it from here. Ooh, yeah. I think this will work. If instead of getting it from here, we can take it from this top one. Alright. Oh, let's remove this. So it should... Hmm. Well, it's copying down. So maybe if we keep it copying from here, and instead of copying this one from, as well as copying it from there, we could put it like this. So if we input it like this, Bro, I also want to make an 8-bit CPU with FPGA and run some sort of minimal command line OS. Is it possible? It's definitely possible, but it's gonna be very, very complex. Wait, hold on, I've forgotten what FPGA is. Like a graphics processing, right? Oh wait, no, it's like an external. Sorry, I was getting mixed up. Why do you want the FPGA? Is that what they use in mining? No, I'm confused again. Field programmable. Okay. Wait. Gate array. Logic bricks. Oh, okay. So it's like a more processing. Yeah. It's definitely possible. Like, I mean, you'd have to. I mean, if you want to make your own CPU, you're gonna use like lithography to etch the silicon, or you could, if you're making it out of gates, and you could have PCBs custom made. It's gonna be quite the challenge, but it's definitely possible. Um. Hmm. Yeah, I don't know how I'm gonna get this one to work. Cause it should be. This one here should be copying it, should it not? It should be being copied before it gets removed. Hold on, okay. Let's shift it. Oh. Give it 1 2. Okay, these delays are gonna take a second. Okay. So what this is doing right now, it's resetting the bottom. Okay. Resets the bottom one. And it triggers this to read from the second one. There's obviously nothing there, so it doesn't do anything. First two steps. Okay, then now it's resetting this third one, and now here's where it should be copying it. Just 50 steps ahead. Okay. Oh. Because we have a data. Could it be the data line interfering? It could be, because now we have 2 inputs. Oh man, it works. Wait, hold up. If we test this, theoretically we could. Okay, no, that doesn't work. Okay, well, this is a breakthrough. Well, I just got a message. No, I didn't. Okay, so look here. If we reset, as long as we have one inputted, once we have one in the line, in a clock pulse, we're getting a toggle with the clock pulse. That's incredible. It should not have been this hard. Wait, I'm just thinking now, like, if we had it on a delay to then reset. No. It's just what starting it up is weird. It's like a car. It's not a perfect clock because it needs to start on. And I don't know how I'll do that because a clock shouldn't have a start. So that's going to be a bit of an issue. Alright, I think it's nearing the end. I'm going to have to go soon. But if you're still here, make sure to like and subscribe to follow along, because this is going to be interesting. We've got a toggle. A sort of a weird toggle. It's very weird. Why wouldn't it work on 2? I mean, I could do something here. I'll really quick make it. Add in a bunch of NOT gates. Why does this 3? It's meant to be a 3 and. Hope I haven't broken anything, but it should be a 3. Where's that counter? No, toggle. No. It's called flip. There. Okay. Okay, so we put this here. Okay, there. That works. Now, instead of having to start it manually, if ever it gets reset, on, off, on, off. Okay, this is the out, and then, yeah, okay, that works. I'm very pleased with this. How about you guys? Hey, super glad. Like, we could use, like, the middle one, but with the first shift, it won't. I mean, we also kind of have no use for a reset, other than to just reset it, but, like, when you start up, I mean, it will reset to 0. So, I mean, we might as well keep it, because you want to know what toggle your toggle is on. And then it's perfect. It's perfect. So, I should on, off, on, off. Oh man, we've done it. This has been like way, way too difficult. Because why the hell is it so big? I actually can't remember how. I'm gonna make a counter. Choma, appreciate your work. Oh, thank you. Unemployed D5. Choma, thank you. Yeah, I'll hopefully make a better explainer video, 'cause you know, can't watch the stream. Here's the ALU. If you wanna see this, so we can do addition. Say 8 and 1, we get 9. We can do yep. Come on, bro. Oh man, I'm tired now. Thank you guys. I appreciate that for watching this far. But I'm gonna go lie down. Does this software let you share chips? Yes, technically. Yes, it does. Join the Discord. I'll send a link. Because sorry, what the hell is this? I'll show you how. I mean, what device you on? What happened? What happened to the chat? What happened to it? Sorry guys, I'm having technical issues now. It just said chat is disabled. Sorry. Bro, if I've disabled the chat, I want to read through this. What happened to it? Sorry guys, I'm having technical issues now. Okay, well it's back. I think I just have to access it on here. Okay, is it? It just said chat. If I've just alright. There's the Discord link. You'll be able to go there. Did your computer engineering degree? No, I'm not a software engineer. Or add your thumbnail. Yeah, it will. Maybe, but people usually see it scrolling through shorts, right? Maybe I will, but I'm just about to end it anyway. I'll make one up. Thank you for the tips. Join the Discord, guys, and I'll show you just quickly how to add chips, because you can find them, well, on Mac. They'll be in a weird folder in your application support. Oh, all right. You have to go into projects. Actually, it will be different on every device. So message me and I'll help. What did I study then? I'm 16. I haven't studied at university. At school, I'll do computer science, but haven't started yet because that's next year. So yeah, thank you guys for watching, and I'll see you guys later. Make sure to subscribe, and I made just some other semi-related videos to this. I'll make some more very, very soon. Thank you. Have a good day.